Carbon capture technology has long suffered from a fundamental identity crisis. Is it a passive filter or an active engine? The stakes here are massive because current methods treat carbon dioxide as waste to be buried, ignoring the fact that we also need hydrogen for fuel and cooling systems, struggle with excess heat. By watching this explanation, you will discover how engineers have revived an ancient chemical trick to create a new class of glass that does both simultaneously. This material transforms from a passive barrier into a functional hardware component capable of trapping gases while managing thermal loads. The breakthrough comes from the University of Birmingham and TU Dortmund, where researchers tackled one of the hardest problems in material science: how to make metal organic frameworks behave like durable solids without losing their porous nature. Metal organic frameworks are crystalline structures with tiny pores designed to trap specific molecules. They have incredible potential for capturing carbon dioxide or storing hydrogen because we can tune those pore sizes with atomic precision. However, these crystals suffer from a critical engineering flaw known as brittleness and thermal shock sensitivity. When you subject them to the rapid temperature changes found in industrial cooling systems or during gas capture cycles, they fracture. They shatter like thin glass when heated too quickly. This fragility forces engineers to keep MOFs locked away in laboratories rather than integrating them into real-world infrastructure where mechanical stress is constant. To solve this, scientists looked back 2,000 years for inspiration. The ancient technique involves a process called fluxing, which has been used since Roman times to lower the melting point of silica and make glass more workable. In modern terms, researchers added small amounts of sodium or lithium compounds to their metal organic framework precursors. This addition acts as a chemical catalyst that fundamentally alters how the material transitions from liquid to solid. Instead of crystallizing into a rigid lattice that cracks under stress, the rapid cooling process bypasses the formation of ordered crystals entirely. The result is an amorphous structure where atoms are locked in place without long-range order. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This ancient flux method reduces the softening temperature of these metal organic framework glasses from over 300 degrees Celsius to manageable levels suitable for industrial processing. That drop in thermal threshold is not just a number, it represents a shift from high-energy manufacturing to low-energy, scalable production. By lowering the energy required to form the glass, we can now mold this material into complex shapes that fit directly onto existing cooling pipes or data center racks without requiring specialized furnaces capable of extreme heat resistance. The resulting porous MOF glass maintains structural integrity even when subjected to repeated thermal cycling, a feat traditional crystalline versions cannot achieve. Now consider how this changes the physics of gas capture compared to what we use today. Traditional methods rely on zeolites or activated carbon, which are effective but limited by their rigid pore structures and lack of mechanical flexibility. When you try to force large volumes of waste gas through these materials at scale, they eventually clog or degrade under pressure fluctuations. The new porous glass offers something different because its amorphous nature allows for tunable pore sizes that can selectively trap carbon dioxide and hydrogen simultaneously within the same monolithic block. This means a single component can act as both a sequestration unit and a fuel recovery system, effectively turning waste gas streams into valuable resources while maintaining the physical strength needed to withstand industrial environments. The most fascinating insight lies in how this material interacts with heat during operation. When carbon dioxide or hydrogen molecules enter these pores, they bind through an exothermic reaction that releases thermal energy. In traditional systems, this released heat is a liability. It raises temperatures and reduces capture efficiency, requiring massive external cooling to compensate. With the MOF glass infrastructure, we flip this dynamic entirely. Because the material acts as both a structural component and a chemical reactor, the heat generated during gas trapping can be actively leveraged to cool adjacent systems rather than fighting against them. This creates an integrated approach where the capture process itself contributes to thermal management of data centers or industrial piping networks. This represents a paradigm shift from post-combustion scrubbing to what might be called integrated infrastructure cooling. Instead of building separate towers for gas capture and separate chillers for temperature control, We now have hardware that performs both functions in one unified unit. The material's ability to withstand thermal cycling without degrading means it can handle the constant on-off cycles of industrial operations where efficiency is paramount. Engineers are no longer limited by the trade-off between porosity and mechanical strength because this glass offers high surface area for gas binding while retaining the toughness required for real-world deployment. However, we must be clear-eyed about the limitations before declaring victory. The reliance on alkali metal additives to achieve these properties introduces a potential vulnerability regarding long-term chemical stability. While benchmark results show impressive adsorption capacities in laboratory settings, there is no data yet confirming how this material performs over years of continuous operation under fluctuating industrial conditions. Furthermore, the production method depends heavily on specific cooling rates that work well for small batches but have not been validated for high-speed continuous manufacturing. We do not know if we can mass-produce these ancient-inspired components at a cost that makes them economically viable compared to existing solutions. The gap between laboratory success and industrial reality remains significant. The rapid cooling technique requires precise control over temperature gradients that is difficult to replicate across the massive scales needed for global infrastructure deployment. Until this scaling challenge is resolved, we are looking at a promising technology rather than an immediate solution. Yet the fundamental engineering logic holds up. By borrowing from ancient chemistry, we have unlocked a new class of materials that bridge the gap between delicate porous crystals and robust industrial hardware. This approach offers a tangible path toward turning waste gas into fuel while solving critical cooling challenges in our energy systems. The journey ahead involves rigorous testing to prove stability over decades rather than days. We need to see if the alkali metals leach out under harsh conditions or if they remain stable within the glass matrix during years of thermal cycling. Scalability studies must demonstrate that we can maintain those specific cooling rates across tons of material without introducing defects. Until then, this remains a laboratory breakthrough with immense potential rather than an installed solution on your local power plant. But for anyone looking at the future of carbon capture and hydrogen storage, it offers a compelling new direction where chemistry meets mechanical engineering in ways previously unimagined. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.